For homework 4, I'm thinking just exploring some tools in Moises, whichever you like. So there are 4 things we haven't tried yet. AI Studio, Voice Studio, Mastering, and Lyric Writer. So just pick one of them and explore. I guess that's the goal of these homework, just to get you exposed to some of these tools and get a sense of what's going on and what are the state of the art and what are something you can do after you've seen these kind of applications. Cool. It will be up and due next Monday or Wednesday. Cool. Um, yeah, I guess we can continue our journey toward latent music generation models. Let me pull up the slides. Um, cool. I mean, we've looked through latent music generation models, but the idea is basically generating music in sort of the latent space. But you can think about it just like a codec. You have like encoded waveform into MP3 codes, bytes, and you sort of want to generate those rather than the waveform. Because think about waveform is like 44.1 kilohertz per second. So that means you want to generate 44.1 numbers per second. It doesn't really make much sense. So that's the sort of the idea of latent space, latent variable generation model. That means that you want to throw it, map the original content into some other domain that's much more compressed and more semantically organized. And then you want to generate those code. And then you decode it back. So this brings us to, neural codec. Basically, those are neural networks that do the job of codec. So basically, those are doing compression and then decompression. And in the neural network space, it's called encoder and decoder because those are basically autoencoder. So that's just a pair of neural network, basically. And you optimize them to do reconstruction so that, codec is built to be as faithful as possible in reconstructing the original sound. So latent-based audio synthesis, basically the idea is just that, well, we turn waveform into some code, and then we want to generate those code. And once you know how to generate these codes, then, during the generation, you basically just grab some random numbers, random vectors, and then you do the generation, you get the code, and then you decode it back. And these kind of, latent-based models are actually some of the, most of the state-of-the-art music generation models are using. And as we talked about last week, Music LM by Google, which is behind FX, and also Audio Gen and Music Gen by Meta, but also, Suno, Udio, lots of, state-of-the-art music startups on generative models are all using these kind of latent-based audio synthesis. So the pipeline is just that, well, we train an autoencoder, we compute the latent vectors. Once we have this trained, autoencoder, we have a codec. So we turn every waveform into MP3, kind of. And then now we want to generate those codes. So we want to train the latent generated models. Once you've done that, then those codes can actually be decoded back to the original waveform. So essentially, you are training these 2 things. One is a pair of encoder and decoder, but also a generated model that generate the codes. So at inference size, this is all you need. You will drop the encoder most of the time, unless you want to do conditional generation. But in this case, you get some code, you get some random vectors, you generate some codes from those random variables, and then you decode it back to waveforms. So we look into this audio gen. It's still one of the few open source models out there for generative modeling. Nowadays, it's highly commercialized. But the idea is that, well, we first train this alkaline encoder so that we can turn waveform into some tokens, as they code it, audio tokens. But you can think about it like an alien languages for audio. So you can sort of think about audio gen as a text to audio model where you are doing this machine translation thing. So the input is like English, a dog is barking in the park. And then your goal is to turn that into some, alien language that's learned by this model. So these tokens are basically the thing you want to generate. So you're going from, English to some alien language. So that's a goal. And this is actually where, Transformer was designed for at first. So Transformer originally was actually proposed for machine translation because you want to handle those, different ordering or different composition, or think about the attention matrix work. You want to know how each word corresponds to different part of the input sentence. So that's essentially what AudioGen do. So basically you grab the input and you want to translate to the alien language. And MusicLM is basically, actually MusicGen is based on AudioGen, but trained on music generation. And there's another model by Google Verse. So basically MusicLM is thinking about how we can generate music from a chords to file generation process. So the idea is that you first get some text semantic understanding of that audio, and then you generate some middle coarse understanding, what we call semantic tokens. And then you combine both of these to generate the actual acoustic tokens. So these acoustic tokens are the code that we are talking about, those sort of like MP3-ish bytes. So this will use a model that's called contrastive learning, contrastive models. And I think that's where we were kind of at. Cool. So this is the thing behind Mulan. So basically contrasting language image model, pre-training clip, as you heard again and again, if you are in this generative field, because that's one of the way to connect text and images. And that's also, part of the technology behind nowadays, text to image generation models. So basically clip is just a pair of image and text encoders. There are two encoders. So you have a cat image and the text cat, and you want to embed those into the embedding space, but same for dog and dog image. So now what you want to do is make the embedding for the cat image and the text cat closer, and same for the dog, but everything else should be further away. So, cat image and dog image, even though they are both images, but they are semantically different. So you want them to be further away. So this is the sort of the idea behind contrastive learning, that you want to, make closer the two different modalities with the same meaning, but within the modality, you sort of want them to be further apart. So you are sort of like generating this, learning this shared embedded spaces for embedded space, one embedding space for images and language. And so that's the same for, CLAP, so contrastive language audio pre-training or contrastive language music pre-training. But the idea is the same, where you want to take an audio or music, you turn them into some embedding space, and also you have text to throw it to some embedding space. And in the end, what you get is just a sheer embedding space for music and language. So now you know that, well, listen to this audio, it sounds like fashionable lo-fi, hi-fi, hip-hop. Then, when you get this music encoder, you throw the things in, and you throw the thing to the text encoder. They should be close in that semantic space. So this allows us to do a lot of things. So think about retrieval, think about comparison, think about, even version identification. A lot of, retrieval-based tasks can be done, but also generative tasks. So that's sort of the idea behind MusicLM, where, when you train these kind of model, you take the audio and you get the Mulan code. So Mulan is the clip for music. So basically you grab the audio, you send to that audio encoder, and then you can get these Mulan tokens. And so you learn to generate, you train these kind of model to go from Mulan tokens to get semantic tokens. And then you combine these two together to generate acoustic tokens. So this offers us a benefit that, during the inference time, now you only have text input and you no longer have the audio input. So what can you do? Because you have this pair of, text and music models. So now you take the text models and send it to Mulan. So now you sort of get this for free. You have this Mulan model that connect text and music together. So now you use the text as inputs at inference times, but you train it using the music as inputs at the training time. So this is actually a lot of, think about DALL-E, think about a lot of image generation of text to image generation model are also using the same idea where, at training time, we use image and use a bunch of audio to grab those latent vectors because we do have these kind of clip models or, contrasting models. But at the inference times, now we only have text as input. But, we don't need to worry about that because those text input can still send to the same encoder, same pair of, Mulan text encoder, and they will be in the same embedding space. So these Mulan tokens should be close. This hip hop song with violin solo theoretically would be equivalent to at the training time you send that violin solo audio waveform into that. So this is actually not ideal. So in real life, there's still a gap between that. So people have to do a lot of things. So actually, there's also additional diffusion prior model. People find out that once you send it to this Mulan text encoded vector, it's still better if you train another sort of neural network to put this and send it to the Mulan music tokens. But anyway, the idea is it's like this, where you get to train on audio but test on text. Or for image generation model, train on image but test on text. So that's the inference time. So these are kind of the backbone models of music LM. Anyway, we've seen these example last week. And also the Google's Music Effect DJ, which is very exciting. So, Magenta, Google's Magenta team, which have been working on music generation for a long while, a decade kind of. So they are recently exploring, this real-time music generation capability, which is very exciting because think about what you can do if you can interact with these kind of models. And so Google's Music FFGJ is one of the sort of like peek into what the future will be like. But basically, it's doing the streaming music generation where you generate the next 30 second, 10 second, and then next 10 second and next 10 second on the fly. And you can sort of like change these composition together. So you can think about, this is just one interface where you just define these words and then you move them around. But think about, in gaming scenario or, real live performance scenario where these things can be controlled by other, potentially gesture, potentially movements, or, based on where you are, like in the map, where you are exploring like an open world game. And you can, for example, enter in another map and then it just smoothly generate the music on the fly and change to another theme of that map. So all sort of these is being explored recently. And you can imagine that if you can make that context window, like 10 seconds into 5 seconds, into 2 seconds, into 1 second, then you are closer and closer to, a streamable real-time music generation system. And of course, this is just not, some techie stuff. Of course, it started as a techie stuff. But, Jacob Collier actually collaborated with Magenta to try out Music Effect DJ. And again, likely a good idea if you want to know how, musicians are using these kind of tool. This is a very good peek into that process. It's very dynamic, very I would say very back and forth interactive rather than, people think about, well, text to music model is just that, press the button and you get the music. But that's usually not the case. You want to get some samples and then you compose on top of that. Cool. So this is like latent-based audio synthesis model. So the idea is just that, well, we can also use spectrogram as the generative results. So we will see in the next few slides about another idea doing the same thing. Cool. Any questions on those? Okay, cool. So those are, think about it like we are using transformer to generate these sort of like thinking about like an alien language thing. So you are generating some tokens. Those tokens are sort of like languages where you just don't understand those languages, but you are still generally one token by the time. But now we are thinking about another perspective where, previously we talked about the sort of like two paradigms in generative modeling, where one is about, transformers for or LSTM, RNNs for text generation, where we think about language modeling that generate one token at a time. And also there's the other paradigm of image generation, where we think about GNNs, VAEs, diffusion models that generate all the pixels parallelly all at once. So this is sort of the next few slides is about this thing called latent diffusion models. You likely have heard it. Like stable diffusion, mid-journey, these kind of everything with stable, everything with latent, everything with diffusion. Nowadays for generative models, 99% chance they are talking about latent diffusion models. So what are these kind of models? It's just diffusion models, but now we have this latent word prefix before it. And as you will see, it is actually a combination of all the things we've saw and sort of image generation. It's a combination of VAE, GN, and diffusion model and transformer actually. So it's a lot. Cool. So to sort of pave the way, we towards understanding what latent diffusion model is. This idea of latent diffusion model actually started sort of from a vector quantized VAE. So these kind of model is a VAE, a variational autoencoder. So you can think about it just an autoencoder where you have a doc image and you turn that into some representation. And now you have the decoder to turn it back. And so this vector quantized VAE is that, well, can we quantize the latent space, this space? So the idea of quantization is that, well, even though for all the image, we can throw it into this latent space, and it could be any places. But what if we only allow it to take certain values? So think about, you throw, billions of images into this latent space, and you will get billions of samples. But now think about these billions of samples. Can you sort of cluster them and make them into, say, 1024 clusters? And you take the centroid of those clusters as the representative examples. Of course, when you are doing the training, you also want to promote the models to cluster them and try to make them, cluster into, 1024 centroids. But that's the idea. That's the idea of vector quantization. So you throw billions of images into this latent space, and hopefully you want them to be, clustered into a limited numbers of possible examples. So this is sort of the idea behind vector quantized VAE. And the idea is that, we allow only a fixed number of vectors to be used in the bottleneck neck layer. And so this allows us to drastically compress the information because now the latent space is discretized rather than the original one that could be any number. Think about float to integer conversion. So now you get rid of all the rounding errors. So now you only get integers. So you get a very, aggressive compression on that. And so VQGN is just another thing, just take this idea further, where now we still have this like VQVAE things, where you get an image and you encode it. And then in the encoded space, again, you do this vector quantize things where these codes can only take one out of, say, 128, 1024 possible values. And then you decode it back. But VQGN basically just extend this idea and leverage the powerful, GN idea. So this thing is called patch discriminator. So, the idea of patch discriminator is that, well, we grab part of the image of the input, and then we see part of the output of the image. And now we are trying to do this adversarial training, where we just look at all the output patches and we see whether those are real. So this is different from the original, GM, where you take this image and see which one is real. Now you are grabbing only part of it. So what's the benefit of that? It's like, well, now these models are not looking at the high level, semantic understanding of this. It's like, is dog kind of in this data set? you are not asking this kind of question. Now you are looking at this patch. Does this hair look real? Does this texture look like a real image? Is the boundary natural? Is the eyes like the structure of eyes the natural rather than very high level understanding of like where the nose and eyes the relative location would be. So now you're looking into zoom in into all the details and make sure those details look real. So that's sort of the patch discriminator is doing. So now you see this kind of idea where GN now take another form. Now adversarial loss is actually being used to improve the sharpness of these outputs. So that's actually how GNNs nowadays exist in modern architecture. So people always talk about, well, like GN, VAE no longer sort of relevant. Now is the era of diffusion model. But if you take a look into some of these diffusion models, you oftentimes, or VAE models, oftentimes you see this VAE and GN turns into another format and still exists. So, in this case, VAE take care of the high level structure of the image, and GN helps to boost those, sharpness of the realness of the details. Actually, nice to zoom in. So each patch is encoded into a latent code. So, when you are doing the CNN, each part of this code actually corresponds to a certain area. That's the feature of CNN, right? You have some receptive field. So think about this 94. It will be these things, and it will be encoded by a certain, n-1 or n different codes. And these are the code books that you can use. And VQGN, the idea is just that, well, they use this transformer then to generate these codes. So once you have these codes, 142, 33, 94, 60, all these code actually correspond to a specific latent vector that could be of any length. So each of this correspond to a vector, and there are 4 by 4, 16 of those. And so the idea of this transformer, the actual generated model, so this is not generated model. This is generated models, but this is not generating new images. You grab a doc and then you get these numbers. This means that you are generating something, right? You basically just know how to encode this doc image. But now how do you generate those? You can actually train a transformer model. This is the things that explore in VQGN, where you take, say we started with 1 or started with an SOS, start of sentence, and then you generate 1, and what will be the next one? And the model learn to see that, well, 42, 3, 3, 94, 60, blah, blah, blah. So you generate images, not images, actually some code as this transformer model, like languages. And these code actually correspond to a certain code book, a vector, and all these vectors together compose this 4 by 4, 16 vectors that you can use to decode it back. So now you get to see these structure become larger and larger. Now you have transformer, now you have GN, now you have VAE all at the same time. But the idea is that this is just sort of the same idea, VQVAE with transformer to generate the internal codes, but also a GN to improve its sharpness. So this is sort of the first time that, we can actually generate very, very high quality images. This is back in 2021, where you can see this kind of conditional image generation models, where this is like depth estimation, depth estimation model. Depth map to image generation. So you take a bunch of image and you generate those depth map, and then you try to train these pair conditional generation. And this is semantic map generation. You will see later latent diffusion model nail it, but this is the first time people can do it. So this is like a blurry image back to more high quality fine grained image sketch to real image generation. Of course, the further away from this to that, the worse the results would be. But we sort of the field sort of get excited about this idea, and the diffusion model comes out. And so people are looking into, can we do diffusion model? Because we know diffusion models sort of like break down this, one-shot process of generating the image into thousands of steps. And that helps. And people figured out that, well, these diffusion models are very good at, generating these very complex um, data. So this is where latent diffusion models come in. But basically the same idea. We first train this VQGM-based autoencoder, where you basically just have some image. So X is the image. You generate some code out from that. And of course, the goal is to generate those code and then turn it back. And everything else is just a latent diffusion model. So, once you have this image, you turn it into some code. And now your goal is to generate this code. So this figure is a little bit tricky to understand, but this is where you will see in all the latent diffusion model paper. But anyway, once you have the Z, then you do the diffusion process. Recall that when we talk about diffusion process, it's about adding noise on the forward pass, and on the backward pass, what we are trying to learn is try to remove that noise one step at a time. So this is the forward pass. You have an image, you generate a code, and you add those noise one step and another for 1,000 steps. And now what you want to learn is the noisy U-Net, where you go from, the very, very noisy input and remove part of that, remove part of that, remove part of that, until you generate a good enough, latent vector. That's the Z. So now you are not generating image, you are generating those codes. But anyway, everything else is sort of similar to what we know in a diffusion model. Inside it, we are doing this, U-Net thing, or you could also use transformer-based architecture. But basically, inputs and outputs is the same size. So you can use whatever models to do that. And of course, we do a lot of conditioning. So this sort of also one of the things that explore in latent diffusion models. You can use all sort of different conditioning to condition this kind of model. So these are like unconditional generation model for stable diffusion. This is the very good quality output. So there's actually a website just like this person doesn't exist, and that's where we get the homework one. Like the list this person doesn't exist.com, I think. I don't know exactly what that domain name is. But you can generate tons of human faces. That's very tricky to see whether it's real or fake. Last year I compiled that homework one, and then this year I totally forgot, and I look into it and I failed. So that's sort of the idea, and you can also generate animal images, but also layout, bedroom layouts, but also landscape image. But more interestingly, these latent diffusion models can also do very good semantic synthesis, and these are seeing lots of recent applications in a lot of different fields. Think about gaming, think about filming, think about video generation. There's tons of application here where you basically just draw the semantic understanding of that. Think about these are trees, these are the lake, water. These could be, I don't know what these different colors are, but these are the skies. So you can see how it generates different version of that semantic layout. It's actually in very, very high resolution, but couldn't see here. But you can check it out. And you can also do, sort of Yosemite-like generation. Anyway, I don't know what this slide is for. So once again, latent diffusion models, we have this sort of same idea, autoencoder turn pixel space into some latent code space. And now we are training this diffusion model to generate stuff in that latent space. So I guess one thing to keep in mind is that these latent diffusion model is sort of like chimera kind of thing. It sort of combines so many different ideas at once, just that, diffusion model is sort of the hot topic then, so it sort of get this name. Otherwise, it could be anything else. So we have this neural codec, which is an CNN-based autoencoder. So we have CNN inside it and trained with a GN like adversarial loss. And we have this VAE idea also in this neural codec. And the diffusion model is applied on the latent space. So once you have this codec, now everything works in the latent space. And so it has denoising UNet. So, it has UNet inside it. And, the conditional model, you do this cross-attention thing. So you have transformer-like cross-attention mechanism. So, sort of everything just come out here all at once. So, GAN, CNN, transformer, autoencoder, diffusion model, UNet, sort of everything we've talked about in this generated fields. But that's how these big diffusion, latent diffusion model is being built. So to leverage everything and all of them sort of like take care of different parts of it where they nail to do it. Question on this, like why? Anyway, so all of them sort of serve a purpose. So, adversarial loss good at capturing those tiny details, sharpness. Autoencoder sort of understand how the big high level, reconstruction. Transformer do the cross-attention thing so that you get good conditioning information into it. Diffusion model nails it in generating very high quality content. In this case, you're generating the latent code, but still you want a very good latent code. And UNet nail it in, something as the same architecture, same dimension as inputs and outputs. And of course, that's based on CNN models. Cool. So there are tons of latent diffusion models for music, and unfortunately, lots of them are actually closed source, because this is like sort of highly commercialized or not highly commercialized or and these very commercialized nowadays. But still, we have this several, one of few open source model in music domain. So, latent diffusion music, this is music LDM in 2023. So the idea sort of will remind you of like music LM or, audio, not audio gen or DALI-like idea where you basically want to train this text to audio or text to music generation model where, you do have lots of pairs of these two things where you have the audio, where you have the text, and now you train this clip model where you learn this shared embedded space of text and music. So what you do is that where you grab this audio, you get the male spectrogram, and now you train this kind of male spectrogram encoder for these VAE models. So you get an autoencoder that's trained on the male spectrogram space. And what you want to do is basically learn to go from text all the way to the VAE decoder. So, during the training time, this is sort of the idea behind DALI and, music LM, where you take music and then you encode it into clap. And now during the training time, you just, once you have this clap model trained on the text music data set, now you apply it to millions or billions of songs. And because you don't really need the text here. You only need the audio and you get the audio encoded, this audio vectors, and you train these kind of model that go from these audio vectors and use the diffusion model to turn it into a code that you can decode it back. And once you've done that, at the inference times, you just look at the text, and now you generate this clap text encoder, you get some latent code. Now you basically just send that out the code because you assume that they are in the shared embedding space. These two things should generate something similar when you have this corresponding, audio and text. So that's sort of the idea behind that. And of course, this is based on male spectrogram. We can listen to some of their generation results. This is not quite as good as our commercial equivalent, but still, this is like an academic version of that. And think about how poor we are in terms of number of GPUs and in terms of data. So some examples. I think I heard some, so we should be good. These are trained on audio stock, like a stop music data set. Q-Toy factory theme. Royal Road, Kawaii Future Base. I don't know what that is. Blast, obstacle. Not bad, actually. Cool. There's also one thing that they explore, which I think is pretty cool. So this idea of turning a poem into music. So this is a very cool like example of how they work. So basically, you take a poem, you get all the sentences, and then you send them to use Music LLVM to generate the music for that. So we can take a listen. Um, well, we basically send the sentence to the model to generate the music for different sentences. Cool. I guess I would just pause it here. I think you get the sense. But anyway, this is sort of the academic equivalent to some of the models that we were seeing, especially now if you play with any kind of music models, it kind of sort of likely to be latent diffusion models or latent transformer-ish models. So these are all sort of different examples of like text to music generation models. But of course, we shouldn't stop at, text to music generation model. There's so many different things we can explore, and text sort of so limited in the sense that, it doesn't fully convey what we might want in music creation. So there's also all sort of different ways of approaching this. So one example that I think we previously talked about is about the VAMNet idea, where this is approaching this idea in a different way, mask acoustic token modeling. So the idea is that, well, this VAMNet is that, well, you take an audio and your goal is that, well, I want to just cover these part, this part, and these part, and to see can we sort of like regenerate those. So how it does this is that, well, we, of course, train these kind of tokenizer where we go from the prompt into, sort of like a time, sort of frequency-ish decomposition where you have coarse tokens and fine tokens. But anyway, you get, 5 tokens at a time and for extended, for different time points. So you get different slices. So think about it sort of like a SDFD where you have all the slices and you get those. What you want to generate is the output where you do have the full understanding of that. And so now you want to go from these mask, blackout, gray out part of it, you want to regenerate those. So this is how you train these kind of model. So you have this neural codec-ish thing here, and you want to train this VAMNet. So VAMNet is doing 2 ways. First, you generate the coarse VAMNet where you only focus on the coarse tokens. And then with the coarse tokens, full coarse tokens, but also the fine mask, unmasked tokens, you generate everything else. So that's sort of the VanMan idea. And they actually explore a way to generate these things. So imagine that if you only have these four tokens at the first, so you want to iteratively do it. You don't want to just generate everything in one shot. So first you generate everything, and you look at those with high confidence, those tokens, or you randomly select some of those. More will likely be in the course part. And then you keep doing that until you reach some confidence on whether those are correct, and then you keep moving on and doing it until you get the full idea. So sample a subset of the most confident predicted tokens in each iteration. So VanMan can actually do a lot of very interesting things. So first, compression, where you just get the coarse tokens and then you recover it. So that's sort of like a easy way to think about compression. You can also do B-driven generation, where you only grab those tokens at the beat. And you can also do impending. We can see some examples here. So the idea of these periodic masking is just that for every period, you just mask out other part of that. For B-driven is that everything other than the downbeat, or beat, you will resample them. Impending is like you just crop up a whole lot of that. So this
For example,
lead us to very interesting demos.
hi, my name is Hugo Flores Garcia, and I'm here to present our
One. Cool. So, the many ways to
VampNet can be
prompt
prompted in many ways.
VanMan.
For example, we can prompt VampNet by taking some input music, unmasking every 13th time step, and then
So, this is just like every 13 of that, you just get one of those. So basically, you don't really get a lot of, information
step.
out of that. So you only get, 1/13 of the input, but you can recover
and then
everything
generating
else.
the rest.
Pretty simple, like redo the revamp original music, which is pretty cool. But you still can hear
Alternatively,
that
we can use a beat tracker
idea.
to locate all the beats in a song and only unmask the tokens at the beat.
So these are where the beats are.
And then have VampNet generate the rest. Or we can interleave tokens from two different songs. And have VampNet generate a mashup of the two songs.
Like switching between two songs.
VampNet can be used as an
And of course, we will talk about this. So it can also generate, used to do this. This is what we call on loop.
we can
But basically, this is like a looper that doesn't, repeat itself. So in every single, iteration, it just sort of generates something new based on the previous loop. So, a looper is something that you just keep doing the same thing again and again. But this is sort of like an expected way that still you are based on the same idea, just that every single time you generate a slight variation on top of that.
This is Unloop. Unloop is a looper that wanders around your original musical idea by
So, the looper that does loop on the original idea, just that every time it's sort of like wandering around that idea. So this is another way to think about, these kind of music generative models beyond the, the paradigm of, text to music generation, because that's not where we want to end. But of course, there's also other ways that is more specific on how you control these music generation models. So, One of the iconic models in image generation model is this thing called control net. So the idea of control net is that, well, can we sort of control our image generation output? Still, these are text to image generation models, but can we sort of like condition them on something? So in this case, we can get the edge or, sketch, edge detection outputs, and in this case, pose estimation outputs. Can we use these as inputs in addition to our text prompts to generate something? So these is likely, you've seen in, Stable Diffusion, Midjourney, a lot of different kinds of models can do sort of something like this. But can we apply that to music? So, can we add controls to a trained text to image diffusion model? So before that, sort of scratch the surface of what control net is doing. So, control net is trying to do the thing is that where, you have this text to image generation model, where there's tons of these kind of, neural network block in your model. And so the idea of control net is that we don't want to use a lot of data to retrain this kind of model, because usually it's much harder to get these kind of pair data to train your model. And you don't want your model to, wander too far away from your original text to image generation model. So your text to image generation model is already working pretty good. You just want to add some additional controls to it. So that's the idea of control net, where you basically lock the original neural network, and now you just want to add some residual information on top of it. So you will take some inputs into that, and you want to add something, you want to compute something, and you want to add it back. So this thing is called zero convolution, which is a convolution neural network that defaults initialized to do nothing. So think about what happened when you first attach this trainable copy onto that. It will basically predict 0 to be added to the original neural network. And so this allow us to, not sort of distract the original models. So the original model would be the same, text to image generation model, just that it doesn't follow your controls initially. Now the model will try to fix everything in this control net, so that you add, some modification to your model. So this is what the control net look like, where, you basically just do exactly the same copy at the right, so that you have this conditional image, and you sort of like similar to UNet kind of idea, where you grab the conditional image and you generate a lot of things, and you try to inference back to the original inputs. So these things are locked. Everything in the left is locked. So originally you have this text to image generation at the left. Now you add this control net sort of plugin on top of it. So it's very interesting to think about, control net. Well, this is like stable diffusion model, and then you have control net attached on that, so that you sort of try to inference it without doing too much harm on the base backbone model. So we've seen this, actually, these the video part, the dancing robots, is actually generated by control net.
Would you hold me tight? How would you touch me? And never let me fall apart.
I was created.
So, you can have someone dancing, and then you get post estimation, and then you regenerate those using text to image models, and so that you can do the controls. So how does that translate to music? So in music, we also have something similar, even though in very, very simple control. That's what we are exploring right now. And hopefully we will see more, fine-grained controls in the future. But, think about, you create these kind of model where you basically have a text to, music generation model. Now you want to control different things. Think about global style control, happy, jazz, blah, blah, blah. But at the same time, there could be time varying control. Think about melody. Those are just piano rolls, or dynamics, where you want to draw a rough curve of that dynamics would be, or think about rhythms where the beat should be. So think about, say video or film scoring, where you want to generate music for a specific video. Then potentially you want to set up the climax where it should be. But at the same time, where these visually where are the downbeats could be. So these control signal could be very helpful in these kind of case where you basically want to generate these control nets so that you generate something that match the original controlling signal. So this is the input and it generates something. And if you check out their outputs, you will see that they actually have roughly the same shape. So here are some examples. We can take a listen. What else? Well, let me grab one of those. Dynamic controls. So basically what you get is like this, like from high to low to high, and this is like low to high to low. You do hear some of those trends. You can also do rhythm controls. It's hard to see here. You can also do melody and rhythm controls. So you have the reference file like this. You can generate. So the model sort of understand how you can apply those controls onto this. So this, another example. And this is the generated music with sad jazz as input. You get a sense. So, still it's doing text to music generation, but at the same time, you have additional controls on melody, dynamics, or rhythm to make sure it works. So if you look at these kind of examples, if you draw this line, you can see that the energy disk goes up, and if you see this melody contour, you can see this melody actually showing up here, and also for the rhythm. Cool. So this is one idea of how you achieve control. But there's also another very interesting idea of achieving control without any training. So this is called inference time control. The model is called Ditto. We will see why it's called Ditto. But the idea of Ditto is now you are not trying to train this model. Now you are sort of like trying to find where in that space will lead you to the desired controls. So, these kind of latent diffusion model is that you will have a latent space, and you have different audio correspond to each of these different input points. And so now your goal is trying to wandering around that latent space to find which one of that latent space will lead to the best, output condition. So think about, you have some certain target features, and basically what you want to do now is try to optimize where you should put that latent diffusion, latent variable as it is. So you can train that. And everything else is just a lot of things. But you can think about this like as, your input is sort of something like Ditto, where you have this, latent code. It could be different shape. And then, imagine that, well, this is our control. We do know we want it to be this shape. So these are your target features. So now your goal is try to just turn these, inputs latent around, move it around and see how Ditto changes shape until you figured out where exactly you can match that shape. And so, turn it into a Pikachu in this case. So the idea of, this inference time control is basically, well, we are not retraining this model, but rather we are leveraging the idea of, randomness and, these variation between different inputs, latent vectors. So we just, explore around and figure out which points actually lead to the closest things to our inputs, and so that you get the outputs. So you can also do some control here. So these are some of the models that you can do. So, if you have this target intensity curve, now you're basically just wandering around that latent space and figure out which one is the best. So this is the best one you can find that sort of has this similar shape. So just, you generate something and, in that latent space, you just figured out that, well, at this point, we do have something that look like this. And at the same time, you could also do this, self-similarity matrix we've talked about, where it sort of indicate what that structure is. So in this case, this is just an ABA case where you have, A, B, and then, this is sort of showing that the third part of that is the same as the first part. There's a repeat. So, you will get this kind of outputs when you do this. So this is the B part, and then back to A part. So you can imagine that, you can just leverage this kind of idea to do a lot of different controls, intensity control, structural control, dynamic, but also, beat controls, all sort of different things. Cool. So just a comparison between these kind of two ideas. So, music control NAT, you need some training. So you need to grab some data to train these kind of models. But, initially it initialized to doing nothing and trying to add those control back. And ditto is another idea where you don't need any training. The idea is just that, well, we're just wandering around that, latent space, try to find whichever latent code leads to the desired feature. Cool. So that's sort of wrap up everything we want to cover in this huge latent music generation part. Questions? Cool. Well, again, this is very, very recent. So if you look at these, both papers are 2024. So people are actually very active researching how to do this. So we don't know yet, and a lot of things could change over the next few years, which is interesting, but also chaotic for me to prepare the slides. So these things will change every single year, but which is fun and exciting. Cool. So what we gone through today, we keep extending this idea of, latent generative model. So the big thing we talk about today is this latent diffusion models idea where, basically the idea is similar. We throw everything into the latent space, and then we try to use a diffusion model to generate that latent code. And of course, you can do some conditioning. But the one thing to keep in mind is latent diffusion model is named as diffusion model because diffusion is hot at that point. But it's essentially a combination of everything we've learned. So, it's a neural code that is CNN based. It's, trained with GN like adversarial loss. There's diffusion inside it, but it only, applies in the latent space, and it's using a denoising UNet. And there's a conditioning module where it's using transformer-like cross-attention mechanism. So it's sort of just everything, from GN, CN, and transformer autoencoder diffusion model to UNet. So, musical DM is one of the way to make it real. So the idea is similar where you train with audio and try to generate a code. But at the test time, you just grab the text and do it again because you have this clap model that sort of have the sheer embedding space. We look at VMNet where basically you just crop out part of the input tokens and then regenerate those. And you can do all sort of like cool stuff with that. You can just crop out different part of it and then regenerate those. But, more interestingly, you could also do a looper that doesn't loop itself. It just generate different slight variation of the inputs. And we're going to look at two specific case of how you can control these kind of like text to music generation models. So one is music control net. Basically, the idea is that where we train an additional pair of models that try to influence the original models, where you take into these controls. And hopefully, once you train these kind of models, the output will have the desired controls. So that's essentially how you train these kind of model. You compute these outputs and you compute how far away they are, and you try to train these kind of models so that it generate the same outputs as your conditions. And the other one that doesn't require any training is that, well, now we just, grab the latent code and move it around, try to see which one actually does better. And we can use gradient descent to do that. So, you grab that latent code here in the latent space, you move it around, and your output will change its shape. The details thing will change its shape, and you don't know what your target feature are. So example, like you want to have it this shape, and you just move that, control then, sort of like knob in that latent space, you move it around, and then this detail will just reshape. And all the way you use gradient descent so that it towards less shape. So all the way in the end, you will get something, in the shape that you want. This is Pikachu. So this is like two different kinds of sort of interesting ways to do it. So music control now, you do some training, but you just get these kind of very fine-grained controls. But ditto, no training required, but sort of you need to pray that you can get something already within your latent space. Sometimes you couldn't get it, but most of the time you will be lucky and you'll get it. Cool. So kind of delay, but that's fine. So next week we could on Wednesday we could look into music production and editing. So this is sort of the traditional way. When you think about music production, this is likely what you've seen, like DAW, auto mixing, reverb, effects, compression. In this case, this is like Max NSP-ish like models. So this is a thing that we will see next week. But basically, it's like, can we generate these, computational graph based on the reference audio? So this is like the dry sound. And so we have this reference audio. And so, the model is just to do the estimation. This estimation is actually not based on the dry sounds. It just listen to this reference file and it can learn to do all these computations. So you will see some other example like auto mixing, mastering, but also, different kinds of things that in the music production side, where, now you've done with the music creation parts, you sort of get an idea what you've composed, you have a music idea, but now once you are in the DAW, how do you actually make them into real life? How do you edit those? How do you do it to get the final outcome?